Okay, let's start. Good morning, everybody. Today I will do a lecture, an introduction to both courses, the continuum mechanics for solid and fluid, and my course related to mechanics of plates and shell. Of course, you know, there are some part of the two courses which are strictly connected. So in this first introduction, I will stress the things that are similar, connected for both courses. So I started to write this hybrid title, you know, mechanics of deformable bodies. Because at the end of the story, we will talk in both courses of this topic. So I will show you, and with me, Professor dell'Isola, how to address this problem, the problem to describe completely the mechanics of deformable bodies. So at the end of the course, we should be able to describe, to define what is a deformable body and what means study the mechanics. And so let's start with this just to explain something about these names. I mean, we have to define what is a deformable body because we are interested to describe the deformation of body, a continuous body. So we deal with solids mainly, but of course, in the course of the dell'Isola, you will see also some application to fluids. And we will deal with mechanics. I'm sure that you already know that mechanics is the part of physics that study the motion of bodies in general. When you study the deformable bodies, you don't study the motion in general, but just some very specific part, some very specific exam. I mean, in many problems that we will deal with, we will study statics, and you know that statics treat a particular motion, the rest. So the idea is to consider a deformable body, apply to this body some external conditions, some external force, and to see what happens. So, in other words, to see the deformation of this body. So, this is a particular situation because we have a reference configuration undeformed, we apply force, and we will see what happened to our body after applying these forces. Of course, in general, we can have also a very complicated motion. So we will try just to describe the deformation of this body without a general motion. I mean, if you have a body without any constraint, you can see that the motion of this body can be very, very complicated. So at the end of the story, we will make some constraint in order to simplify the analysis. Of course, there are a lot of applications, and we will see what applications. Then are important for that are to be considered to have just the study of the deformation in a static regime of our body. And for this course, I think that we will study just the statics. Maybe in the second semester, I will do something about the motion and the vibration, small vibration around an equilibrium shape of our bodies. But we will see later this kind of stuff. Let's start with the simple object, the simple topic of deformable bodies. First of all, we have to make some general consideration about this problem. And I will talk, especially today, of what a model is. Because this part is very important to understand not only what we are doing, but also how to build the model itself, because in this way you have a way not only to see, a classical model, but also a way to develop new models. And you can understand that this will be a very powerful tool if you manage to understand how to build a model. So let's try today to have a general glance of what a model is and how to deal with the issue related to this kind of abstraction. First of all, I should say a model is an abstraction, a concept, a mathematical tool, if you like, that allow you to represent a real phenomenon. But the idea is not to represent the real object, the real phenomenon in all its details. We will try to keep only some aspects, some detail that we want to consider. So, in order to build a model, first of all, we have to consider a real object, to study this real object, to observe this real object, in order to understand what kind of simplification we can make, what we want to describe of this real object in order to make a model. So what I want to underline is the fact that in some sense, you have the real object, which is something, and then you have the model, which is something completely different. So you have to consider these two words, the real one, and the word of the model, as two separate things. Why? Because you can have that the real object can be modeled by different models. So if you confuse the real object with the model, you can be in some case, you can have some troubles because you confuse the model with the real object. But if you consider that they are two separate things, and the model is able just to represent some case, some particular case of the real world, you will see that with different model, you can see different things about your real object. So this is just a general view, but it's important that you understand that there is the real world and is the real of the model, the word of the model, then which is a mathematical tool, something different from the real object. Why I tell you this? I'm sure that you already know from the course of physics that the real object can be modeled in different way. Let's do the example of the Earth. EH. You know, the real object Earth can have a different motion, and depending on what you want to describe, you can use different models. I mean, for example, if you are interested just to model the motion of the Earth around the Sun, you can imagine to treat the Earth as a material point. I'm sure the material particle. So you consider the Earth as something which is represented just by a point in the space. This is, of course, the most simple model that you can use to describe the motion of the Earth. But look, this just is able to say what is the position of the Earth with respect to the Sun. If you are interested to see other phenomena, I mean, for example, you want to understand the alternation of the day and the night or the season, you have to consider the Earth as a body with some sides different from zero. It's important to understand what is the angle between the axis of the Earth and the how the direction of the light coming from the sun. I mean, if you want to understand the day and the night, or if you want to understand why you have some season, which is the summer, some season, which is the winter, just because the direction of the radius of ray from the sun are different. So of course, in this case, the material particle cannot be used. You must use something else. And the simplest model to do it can be the rigid body. So you can imagine the Earth as a sphere as a first approximation with some dimension, more or less the dimension of the Earth. And so you can treat the motion of this rigid sphere in the space. So you see, these two models are quite different because in this case you have just a point in the space. In this case you have a sphere that can rotate. So you add at least 3 degrees of freedom to your system in order to describe something more. But this is not all. For example, if you are interested to understand what happened in an earthquake, you have some deformation of the earth. You have some kind of wave that transmit in this deformable body. So, of course, if you consider the model of rigid body, you are not able to describe this kind of phenomenon. So, if you want to study on the scale of the Earth, of course, this kind of phenomenon, you have to consider a deformable body. To describe the motion of the Earth. Of course, this is a little bit more complicated than this because you add degrees of freedom to your model. So with this model, you are able to describe this, but also something else. And here the same. This model is much more complicated than a rigid body because you can model with this model the same thing that a rigid body do, but also something else, the deformation. The fact that you can have some wave propagation inside the body. So you can study what happened to the Earth during an earthquake. So you see, with this simple example, there is just one real object, the Earth, but you can apply to this object different models because with different models you can see different outcomes, different aspects of your phenomenon. So at the end of the story, when you build a model, you have to keep in mind what is the aim of the model. The scope, the end of the model. So we have to ask ourselves this question. The model, every model, has the aim to predict some outcome of a real object. You know, I underline some aspect, some outcome, not all. So, depending on the phenomenon that you want to consider, you can decide what is the important outcome. And the idea is that your model is able to predict this outcome. So you know before that this outcome can be measured in some real observation through some calculation. And this will be very powerful if you want to use your model to design something. I mean, a structure or a machine. If you know how to work your structure, your machine, when this structure can have some broken part, of course, you can improve the design of your system before to make some experiment. So this will be a very powerful model, a very powerful tool. And what we try to do in our course is to build a model, few models, we will see some example, that are able to describe deformable bodies in some particular situation. So you will see that the same object can be described with different models. Of course, this depends on what we want to describe. And with these models, we can understand what happened to our system before that this really actually happened. So the idea that we have in mind is this one. We start to observe the real world. Okay, so on the basis of this observation, we have to focus on a particular phenomenon. On the basis of this consideration, we will consider some object that are the first ingredient of our speculation. Of course, something is the real world, something is the world of models. So we have to consider some relationship between the real object and some concept which can be used to describe the real object. So you see, in the case of the Earth, we talk about points, rigid bodies, deformable bodies. So some mathematical, geometrical, in this case, object that you can use to describe the real object with some limitation, with some simplification, of course, because we don't, I mean, you know, I'm sure that here for the Earth, you can use in this first approximation a sphere as the shape of the Earth, but you know that the real shape of the Earth is much more complicated than a sphere is something like this. It's more like a potato than a sphere. Yes, if you saw the Earth from the moon, for example, you are not able to see the difference between the real shape and the sphere. So in first approximation, you can use the sphere, but if you want to consider, I mean, some phenomenon for which the shape of the Earth is important, you must abandon the simplification of the sphere and consider a more accurate description of your object. So, you know, depending on what you have to describe, you can define in the mathematical world some set of objects that is able to describe your system. And from a mechanical point of view, so you have this object to deal. The real object are bodies at the end of the story. The mathematical tools are geometric entities, which can be a point, set of points, volumes, but also in some particular case, you can talk about surface or line. If your body is very thin in one direction or in two directions, you can imagine to describe your body as a surface or as a line. So you can imagine that instead of considering a three-dimensional volume, and this can be in some case unavoidable, but sometimes you can simplify the geometry and you can talk about planes or some kind of surface, I mean cylinder or sphere, or lines. So you can talk about plates, shell, or beams, which are 2D or 1D entity, mathematical entity, which are able to describe object with a particular shape. So we can simplify in a way or another the geometry of our system, the object that we want to study. Then what happened? In the real world, you have that many objects can interact. Each other. And these interactions are the responsible for the motion. You know, if you have two objects, these two objects can be in contact each other, or you can have also interaction at distance. This kind of interaction are the cause for the motion at the end of the story. So the results of this interaction will be the motion. In general, a motion is nothing else than a collection of configuration over the time. So if you want to study just the statics, the motion is simply the configuration at rest after you apply some forces, better after that some interaction happen between the object that you want to study and the rest of the world. Fine. In the mathematical world, we have to reproduce this kind of stuff. Of course, when we say the real object have some interaction, this is in the real world. Then, in the mathematical world, we have to define some concept, which is defined here in the set of objects that we want to study: material particles, rigid bodies, or deformable bodies. And this concept leads us to define some mathematical concept like forces, moment of forces, and other that you can add. Of course, you can add depending on what kind of object you define at the beginning. Of course, these objects are not the interaction in the real world, but are some mathematical concepts that we introduce in the set of concept mathematical abstraction in order to have what reproduce the interaction in the real world. Introducing this concept, we are able to obtain also in this case some result. what is the result in this case? The result in this case is some plot, some function. We give you the configuration of your system with the hypothesis that you consider at the beginning. So at the end of the story, your model is good if the results that you obtain, so the motion in terms of displacement, the motion in terms of velocities, something like this, correspond. So if this is true, you can make some kind of relationship between the real object and the simplification and the geometrical object that you treat in the models. If you have some kind of relationship that link together the interaction, the real interaction with this abstract concept that we introduce to reproduce the same outcome, then you are able to obtain some results in the mathematical world, the motion in the real world. Of course, your model is good if this result and this motion can be considered equal. I mean, equal in the sense of you made some measurement, and then you can say if these results are very near to the real thing or they are different. Of course, if they are very real, very near, you are happy, because without making any experiment, you will see what happened to your system, to your object, at least in the hypothesis that you make at the beginning in order to obtain this result. Now, okay, this is fine. Everything is based on this kind of scheme. Many models are built in this way. When you do this, at the end of the story, you can have three outcomes. So let's make some examples so you can understand how this kind of problem, how this kind of vision could be applied. I mean, the first thing is, okay, the results coincide with the motion. And this is the most important part, of course, because this means that your model is not so bad. But you can have also, in some case, that the results are not the same of the motion. You see, this is a bad thing. But not always is this kind of mismatch is a bad thing. And now I will make two examples that explain better this kind of situation. The first example is the discovery of Neptune. You know, the planet. I will tell you this because this example is very instructive to understand what is a model and what kind of problem you can face when you build a model. One of these situations is given by the story related to the discovery of Neptune. If I recall well, should be something in the 1846. So it's quite recent if you if you think about it. But I want to underline two things for you. One is that Neptune was the first planet that was discovered by a mathematical model. It's not because someone point the telescope in a certain point of the sky in the night and saw Neptune. To be honest, I have to say that Neptune was seen before the 1846. Someone compare a drawing made by Galileo Galilei when he invented the telescope. So we are in the 16th century, much more before of the discovery of Neptune. And if you compare the disposition of the position of the point that Galileo drawing in this observation of him, you can recognize that one point occupy the position of Neptune. So Galileo indeed was able to see Neptune 2 centuries before the discovery. But Galileo Galilei confused Neptune with a fixed star because he didn't have the theory that tell him, look, this is not a fixed star, but it's something else. Indeed, is a planet. So he confused Neptune with a fixed star. But let's go in the detail in the discovery of Neptune so you can understand better what happened. The issue before this date was the orbit of Uranus, which is the giant planet that before of the discovery of Neptune was the last planet of the solar system. The point is that when one applied in that time the classical mechanical theory, I mean the Newton laws at the end of the story, what are known as the Newton laws, they simply saw that the orbit of Uranus was different from what the theory of the classical mechanics predicted. So we are in this situation in which you have a model, the classical mechanics, the real object. The real object is Uranus. The orbit, so the motion of Uranus, is not coinciding with the orbit predicted by the classical mechanics. So at this point, people have two choices to consider. One is that your model is wrong. So in some way, this means that the hypothesis that you build, you consider to make your model, in some way are not satisfied. So because at the end of the story, you start from some conjecture, you start from some hypothesis, and then everything is rigorously obtained by mathematical calculations. So since logic is, always correct, what can be wrong is what you fixed at the beginning, so your hypothesis. If some hypothesis is wrong, of course, the result will not be the same. So this is a possibility. The classical mechanics is wrong. Is wrong in the sense that the hypothesis that you made for building the classical mechanics in some way, in this case, are not satisfied. But people in this age cannot say Newton is wrong. Newton is considered like a god in this epoch, so you will understand that they choose the other possibility. The other possibility is this one. If the results do not coincide, can be another phenomenon that we are not aware of that can change the orbit of Uranus. So they said, okay, if the orbit of Uranus is not what is predicted by classical mechanics, should be somewhere near another planet with another orbit, of course, that perturb the orbit of Uranus. And so this is the reason why the theory fails, because we do not consider the correct input of our problem. Of course, if there is a planet that you don't consider this planet, the orbit of Uranus will be different. This is clear. So, one guy from France, Leverrier, said, since the classical mechanics should be correct, the only possibility here is to explain this behavior, saying that another planet is there for which we are not aware. And if we predict, we evaluate the orbit of this new planet in such a way that we correct properly the orbit of Uranus, we can predict where this new planet is. And so astronomer, a German guy in the 1846, starting from the prediction made, the calculation made by Leverrier, effectively saw something, and this was the discovery of Neptune. To be honest, there was a dispute because some French said that the first guy to make this calculation was Leverrier, but as always happened in these cases, there was also, if I remember well, Adams, a Briton scientist, which more or less contemporarily make the same calculation. At the end of the story, they decide that they both make in an independent way this calculation. So the discovery of Neptune is related to both guys, the French one and the British one. You know, this is just to say that sometimes it's difficult to say who is really the man that discovers something. But at the end of the story, this is an example which is very interesting, because you see, a real good model is a model that allows you to if the hypotheses are correct, predict some phenomenon which is a new phenomenon. In this case, they using the classical mechanics was able to discover Neptune. Just from this situation, this odd situation for which the orbit of Uranus, the calculated one, was not in accordance with the theory that was considered the right one. So, you see, this is one example. The other example, of course, you understand now that the other example happens when the hypotheses are wrong. And after all, the same example can be done using the classical mechanics and the planets, also to talk about this other situation. The case was made for what happened to Mercury. The planet Mercury. The question is this: also for Mercury, we have that the orbit of this planet do not coincide what the prediction made using the classical mechanics. So you can imagine people making this calculation and showing that this is not correct, make another time the same choice. I mean, here, as before, you can have two possibilities. The classical mechanics is wrong, or there is some other thing that we do not consider. And was the same Leverrier that said, okay, maybe it happened the same. So between Mercury and the Sun could be that there is another planet. They named this planet Vulcan. Should be something like this, Vulcan. Also in this case, they consider the name of a Latin god. But nobody from this time after the discovery of Neptune and today, nobody is able to see this new planet, Vulcan. By the way, the international end for the astronomy thing deserve this name Vulcan to the hypothetical, today also, to the hypothetical planet that can be between the Mercury and Sun. But this is not the case, even though this name is deserved for this planet that there isn't. What is interesting in this case is the fact that if you abandon the hypothesis of classical mechanics, so and this calculation was made by Einstein with the general relativity. Using some hypothesis, which is different from classical mechanics, the hypothesis of general relativity, Einstein was able to recover from his theory the correct orbit of Mercury with a very, very small error. So you understand that now changing the hypotheses that are behind your model could fix the problem. The idea is simply that in the classical mechanics, when you describe the geometrical space, you use simply the Euclidean geometry. So the standard stuff that we are all accustomed with. Instead, the fact that Mercury is very, very near to the Sun, which has a big mass, changed this aspect. I know that you for sure hear that when you talk about the general relativity, you can talk about a warping of the space near the stars, simply because the stars are a very big mass. So near the Sun, very near the Sun, for the mass of our Sun, the geometry is a little bit different from the Euclidean one. And if you make the hypothesis of Einstein, typical of the general relativity, you will see that the orbit of Mercury is can be calculated with this new framework. So you see, in some case, and this is the case of Neptune, you can imagine that there is another phenomenon that you don't know, and you can discover this new phenomenon because you are confident that your theory is good enough. But sometimes you cannot, because this new phenomenon is not there. You cannot fix the problem in this way, so you are obliged to use some different hypotheses. Now, what I want to underline here is that the hypotheses made by Einstein, which are the base of the general relativity, are more general of the classical mechanics. What means this? That with the hypothesis made with the general relativity, you are able to describe a set of phenomena much bigger than the phenomena that you can describe with classical mechanics. So you have something like this. This is the set of phenomena that you can describe with general relativity. This is the set of phenomena that you can describe with classical mechanics. You see, it's a subset. And what is important is that when you are able to make this generalization, there is some phenomenon that can be described because there is a superposition of hypotheses. So the hypotheses are more or less the same, are better. The hypotheses are both satisfied in this case. So in this case, the outcome of your model, classical mechanics and general relativity, are exactly the same. So at the end of the story, you can study the motion of the other planets, which are far from the Sun, the Earth, the Mars, the Uranus, and so on, with general relativity. You can do also with classical mechanics. So one can say, why do not use general relativity? Because in this way we can describe everything in the solar system. The problem is that classical mechanics is easier than general relativity. So it's true that if you change the hypothesis in this way, you can you change the hypothesis, you can describe more phenomena, but this means also that you add some detail to your problem, to your model, and this will complicate the things. So solve the problem with the general relativity model is more complicated than using classical mechanics. So the idea is we do not discard completely the classical mechanics. When the hypotheses of classical mechanics are satisfied, we continue to use classical mechanics, simply because the model is easier, so we can obtain the results in a much simple way than the general relativity. When we must study Mercury, the hypotheses of classical mechanics are not satisfied, so we switch off and change the model that we can use, and we will use general relativity. So you see, in this framework, we can able to improve our modeling possibilities, simply looking to the hypothesis, and we, at the end of the story, see if this link is satisfied or not. This kind of approach is called that we can, in this way, falsify our model, possibly. So we said, if the hypotheses are correct, we will see that our model will not be falsified. If something goes wrong, we can say the model was falsified. So in this case, we have to change the hypotheses that are the base of our model. So you see, when we reach this situation, in some case, as in the case of Mercury, this is what happened. In this case, we must improve a little bit the hypothesis in order to regain the correspondence between result and the real motion. If we talk about mechanics, of course, if we talk about other kind of models, the outcome will be different from the motion, but at the end of the story, this is always what we are doing in our consideration about models. The fact that a model can be falsified is very important, because always a model is defined by its range of applicability. I mean, when you use a model, you must be aware that this model is not able to describe everything. Can be used only in particular cases, the cases for which your hypotheses are satisfied. So when you reach, in some example, this condition, you falsify the model, you can set what is the limit of your model. You can understand why the hypothesis is not satisfied, and so you can say, okay, from this point on, I need to change a little bit the hypothesis in order to make better our model. So you see, the fact that the orbit of Mercury is not prescribed by the classical mechanics, simply imply that we have to change the hypothesis, so we can use the model of classical mechanics for all the other planets which are sufficiently far from the Sun. So starting from Venus and the other planet, we can use classical mechanics because the hypothesis of classical mechanics are valid. For Mercury, not. So you see, you falsify your model because the orbit of Mercury is not the one predicted by classical mechanics. And this falsification allow you to say, this is the limit for the classical mechanics. After this limit, I have to change something. I have to improve my model. And I can do it using, for example, general relativity of Einstein. So I can consider this process of falsification as a test, as a tool, which allow me to understand what is the limit, the range of applicability of our model. So you understand that this is very important, because if you have a model and you don't understand what is the range of applicability of your model, you are not sure that your result will be predicted, that your result will be the same that the results of the real world. So this is a very important issue when you build a new model, of course. So this is just a general picture of how a model can be thought. Of course, we talk about mechanics, so in all the models that we will see in the future, we will follow all these steps. We have to set some initial hypothesis in order to fix what we are able to predict. We must define in some way how to describe the object that we want to consider. We have to introduce something that is able to mimic the interaction of your object with the rest of the world. And so, based on this initial definition, initial assumption, because the hypotheses are assumptions, we will see the results. And we always have to consider the comparison of the results with some experiment in order to see, okay, my model can be correct or not at the end of the story. So these are always the steps that we have to do in order to consider the models that I will show you. We will start to consider the very general situation in which we will define a three-dimensional deformable body, and then we will introduce some other model which are a simplification of this. We will talk about the beam models. There are at least 3 models that are able to describe the easiest one. The behavior of one body which mass is distributed along a line, more or less. So the other two directions are so small that we can neglect the other two directions. This is the fact. And so I will describe you how to build this simplified model. And of course, we can do the same when the mass of your system is distributed on a plate or a surface. So we will talk about models which are able to describe the deformation of plates and shells, of course. So we will see all these models. So I always will make these steps in order to describe this model. So you will see always the same procedure. Of course, case by case, this procedure will be applied with different hypotheses, with some small difference here and there. You see that the interaction will be different because the model is different, and so we will go into details of this stuff. In particular, when we talk about simplified models, so I mean, instead of a body, when we draw a generic body, we always draw something like a potato. Of course, you can describe a three-dimensional model which is able to describe the deformation. And we will see how to build this kind of model. But you understand that, let's say, for example, in the case of a beam, you have a real object can be like this. So you see, there is clearly something like an axis. And then the orthogonal direction to this axis, this one and this one, are very small with respect to the length of your body. So clear, in this case, you can introduce a geometrical entity, we describe your system, which is 1D. A body which is monodimensional. So you can make a model for this particular situation, for this particular system, starting from the scratch directly. So you define what is the representation of your beam at the end of the story. You define what are the possible interactions, and then you will build your theory directly, and we will see how to do it for the case of the beam. In the case of the shell and plates, this is a little bit difficult because you need some introduction of differential geometry, which is too complicated, I mean, for the time that we have. So I will follow another path. We can also make a model starting from the general framework of the 3D and simplifying this model. So starting from the model which is able to describe a 3D body, we can make some simplification and obtain a reduced model for 1D and for 2D, and we will see how to make this reduction, because, you know, this can be very helpful, especially if we want to see what happened to a plate or a shell. So this kind of reduction will be very useful for us. I will show you how to do this. Okay. I do not want today go into this detail, so I want just to give you a general glance of what we have to do. Of course, when we describe, we build a model, and this model is a mechanical one. At the end of the story, we will write some equations that we have to solve. This is more or less the end of all problems that we will handle. We have to solve these equations. In some very simple case, we can solve this equation by hand, but we have to make very drastic simplification in order to do that. We have to consider only linear models in which all the coefficients are constant. Also, the geometry is uniform all over the system. So you can understand that with this very strong simplification, you are able to solve this problem. But in general, and for many applications which are important, you cannot do this by hand. So what I will introduce you in these courses is the use of a method to solve the equation. And this method, when we talk about deformable body, is the finite element method. The finite element method. In this semester, I will just show you how to use the software, and the software that I consider is COMSOL. So we will see some results from the model that we build. In the other semester, that in the course of computational mechanics, I will go into details from a theoretical point of view. What is a finite element method? What means that we have to make an approximation of the solution in some way. In these courses of the first semester, I will just give you some general information in order to go ahead. But we will go into detail in the other course, computational mechanics, because I want you to describe, to explain what is the theory of finite element method. You know, this kind of method is very popular nowadays, so it's important that you understand what it means and how to use properly this kind of method. COMSOL is one of the many commercial software that are able to solve using the finite element method deformable bodies. I mean the shape of deformable bodies. We can use console in two different ways. I will show you both. One is to use what is the structural mechanical tool. So all the models that we will see, will obtain in our course are already implemented in console. And so you have just to use console as a user. You have just to know what kind of input console needs in order to get the results. And this is more or less all the story. But this is not very important to me because, you know, this is like, some field, you know that you have to give console some field and you can obtain the results. So it's not an important stuff from a theoretical point of view. What is interesting is the fact that in console, you can write your own equation from the scratch using a basic tool. So all the models that we are able to write in our course can be programmed from the scratch in console. And I will show you how to do this because, of course, these are classical models, so you can use both situation, the structural mechanical tool and the basic tool, and you can obtain results. But the important thing is that if you have some new model, because you want to be a researcher and you want to build a model which is not in literature, something new, you can do it using the basic tool. So you can solve potentially every model that you can imagine in your mind. So this is a very powerful tool. Of course, this tool is not optimized for everything. So you can have some results, maybe you have to struggle a little bit to have the results. But this is not the important stuff. I mean, the important stuff is that using console, you can have a quick glance of what can be the results of your model. So you can make some adjustment in the hypothesis, in what is important, what is not important, what is negligible, what is not negligible. So you can improve your model, and then you can ask some informatic guy or some mathematical guy to make a software which is optimized for your model. So you can use console as a tool to build the model, simply seeing some results. And this can be very, very useful because with few passages you can have some results sometime. So this is important. And the other feature that can be interesting of console is the multi-physics. What is the multi-physics? Is the fact that console allow you to make together many equations. So you can talk about mechanics, thermic effect, electric effect, acoustic effect, fluid effects, and so on. all together. And this will be very difficult with other software. So this is another important stuff that you find in console and you can use in whatever you need to consider. So this is, I will show how to use this kind of stuff, even though I will concentrate mostly on this part, because using this part, I can explain you what is the problem that are behind the numerical implementation of your model. What are the important things that you have to consider in order to obtain the results? Because for different models, you have to use different discretization. So you have to know what kind of discretization is good for a model and what kind of discretization is good for another model. In this part, everything is already set as default. So you can use this part even though you are not fully aware of what you are doing. Of course, this can be useful for an expert user, but can be very dangerous for a user that is not fully expert. Do you understand? So I will try to underline all the important stuff that you need to know in order to get your solution, and in order to have a solution which is with certain satisfaction correct. Okay, and this is also something that I want to talk about. And the last thing that I want to talk to you today, we have just 2 hours, so I do not make any pause today. At the end of the story, we make just a very long discussion about what we have to do. So it's just an introduction. You don't be afraid. We will see in all the details in the future lecture. The other thing that I want to underline today, and I will finish with this, is that when we talk about mechanics, we have 2 possibilities to go ahead with our modeling procedure. I mean, and maybe you already saw this kind of point of view. You can say one possibility is considering as a fundamental hypothesis the fact that your body is governed by the conservation of energy. Since we talk about elastic deformation, conservation of energy is a fundamental tool. And you can use the conservation of energy to build your model. And we systematically use this principle, the principle of conservation of energy, to build everything. Even because the approximation made by finite element method is based dramatically on conservation of energy. Everything is conservation of energy. So if we start with this concept, we will adapt very easily to the tool that we will use with the finite element map. I will show this kind of stuff. The other possibility is to start with the framework of the Newton laws. You know, the first law, the second law, and the third law of Newton. That in the case of, and the important stuff in the case of the mechanics of the form of a body are the balance of force and the balance of moment of force. So in this framework here, you postulate the conservation energy, and everything comes from this postulate. In this other point of view, you postulate at the beginning the balance of force and the balance of moment of force. Now, of course, both methods has advantages and disadvantages. To be honest, this method has many advantages than disadvantages. But anyway, for being complete, I want to tell you both of them, even though I will concentrate for the most part of my time, and the same will do Professor Dell'Isola on the first method, because this method, the first one, is more general than the other one. It's more general, and we will show you why this method is more general in some sense. Even because for certain material, the balance of force and the balance of moment of force is not enough. So you have to introduce something else, and you know, it's not easy to deal with generalization in the case of balance of something. Okay, so we will understand better this kind of stuff. Just now we have a few minutes remain, so I want just to underline what means the first one, and what means the second one, with a very, very simple example, so you immediately know what we are doing. Let's consider this simple model. We have a spring. Let's call this spring K. This spring is linked with a mass M on plate. I'm sure that you already saw this kind of simple model in which you have a mass that you can, in this experiment, treat as a material particle, and a spring that connect the mass with the ground. That's all. You saw the equation of this system. If you consider just the static, it's quite easy to write. But I want to show you how to do it for the first, in the first framework and the second framework, so you can understand better the difference between the two words that we have to use, we can use in this modeling stuff. In the first case, of course, for both cases, you have to describe the motion of the mass, this material particle, using a reference frame. So you introduce a reference frame. You can say here there is a variable, let's call it x. And if you know the position this x, you know everything about the motion of your system. You can think about applying to this material particle an external force. I have to define what is a force, but anyway, I can use these customary words today, and the idea is, okay, what is the static deflection of the spring under these circumstances? So you apply an external interaction, let's call it F. The spring will elongate. So let's find the X that that represents the equilibrium of this spring. A possibility is simply, let's define the elastic energy of the spring, and you know, in this simple case, the elastic energy related to the spring is 1/2 k x squared, because x represents also the deformation of the spring. But this is not enough to describe our system. We have also to consider the potential energy related to our external force, so the energy associated to the force. The potential energy associated to the force is nothing else than the work done by the force, but we have to change the sign to this because we have to consider the energy, not the work done by the force. So minus Fx. You know, this is simple physics. So the total energy of our system is the sum of these two contributions, 1/2 k x squared minus Fx. This is the total energy. The principle of conservation of energy tells us that the equilibrium is reached when this function, the total energy, reaches a stationary point, in particular a minimum. So the idea is to find the minimum of this energy to find the equilibrium x for this spring. So at the end of the story, using this setting, we are simply to make a derivative of the total energy, and with this derivative, we will find the equilibrium configuration. This is simply the derivative of the total energy with respect to x. Of course, the derivative is this one. The stationary point is given when this derivative is equal to 0, and so you know that the solution of our problem is this one. Useless to say. So the spring will deform of bar x, where bar x is F/k. And I will show you that we will systematically use this kind of conservation of energy, find the minimum of the total energy for all the model that we will define. So this is a possible choice. Now, for the other possibility that we have, we can say, okay, let's consider what is called free body diagram. In this case is a free material particle diagram, because this is just the body that we have to consider, and to consider on this particle the external action that act on this object. So we have to do exactly the same for describing the kinematics. So we have to define with a reference frame the variable x, which represent the motion, I mean, of this material particle. And then we have to put on this material particle the external action that act on this. So we have the same as before, F, which is the external force that we know, and then we have the elastic reaction. Now, instead to consider the energy for the elastic part, we will use the Hooke law. So you know the constitutive equation is the same that give an elastic energy at the end of the story. The Hooke law tells us that the elastic energy, the modulus of the elastic energy is kx, and the direction is given in such a way that the force will oppose to the deformation of the spring. So in our case, if x is positive, we have that the elastic force is minus kx, oriented in the other direction. So minus kx is the algebraic component of our vector force, elastic vector force. So at the end of the story, using, in this case, we have just a material particle, so we can use just the balance of force. And the balance of force tells us that F, you see F in the positive direction, the same of the displacement, plus minus kx should be through the balance of forces. In this case, the static case, all the forces that are applied to the material particle are these two, the external one and the elastic one. So this must be equal to 0. So you see, someone in the past, being a little bit smart, said, okay, for the conservation of energy, I always obtain this. So why I do not make the hypothesis that the balance of force is always true? And so, without make the derivative, because sometimes this derivative can be difficult, this is the reason, they postulate at the beginning directly the balance of force. And so, at the end of the story, in this case, also in this case, we obtain, of course, the same result. Now, of course, we always can choose one way or the other to solve our problem. But anyway, there are some difference between these two ways to think the problem. Let's say, for example, here in this framework, you have to deal with an energy, and an energy is a scalar quantity. I mean, I am happy to deal with a scalar quantity because I do not have to consider projection of vector or some complicated stuff which can be vectors, I mean. So it's clear that a scalar quantity is better to use than a vector quantity. Instead, in this way of thinking, this problem, you have to deal with vector quantities. So, of course, every in every situation you have to make projection, you have to see what is the sign of this, what is the sign of that. This can be very difficult sometimes. So this is one stuff that we can say. Of course, why people many times prefer this kind of point of view instead of the other one. Because when you talk about balance of force, at the end of the story, you obtain something like this, which is an algebraic problem. Even though this is just an intermediate result, because then you have to solve the problem for the displacement. Sometimes, of course, solving an algebraic problem is simpler than the other stuff, because here, instead, in order to have your results, you have to solve a, for continuum problem, partial differential equation. We will see all this in detail, but the problem is that here you have a partial differential equation and you have to solve the partial differential equation. Here you can have some intermediate results on force that you can obtain simply with algebraic calculation. And you understand that algebraic calculation is simpler than solving a differential problem. So this is the reason why many people use this kind of way to think mechanics instead of this one, because they are afraid to solve partial differential equation. But the problem is that using this way of thinking, sometimes you can obtain some wrong results if you are not careful. I will try to explain this stuff because this point is very delicate. The idea is this one. When you define balance of force and balance of moment of force, when you treat a continuum body, you are nothing to say from the start about what can be the boundary conditions. So at the end of the story, you have to postulate the boundary conditions in an independent way. This can be difficult in some case. Instead, using this framework, we will see it's very easy. From the conservation of energy, you get also the boundary condition automatically. So you have not to do any other independent assumption. And you can understand that when you make many independent assumptions, you can have some trouble, because if your assumptions are not consistent, are not coherent, you can have a mathematical problem which has no solution. You see, this can be a problem. Why I tell you this? Because many times we will face this kind of situation. For continuum body, this is this is the usual thing that we have to face. Let's make an example so you can understand better this, and then I will finish in a few minutes. Consider an ideal fluid. You know that in an ideal fluid, the only interaction that you can have is an external pressure like this. This should be orthogonal to the surface. Why? Because the ideal fluid can support only compressive stress, can deform only in an hydrostatic way without any shear resistance inside the body. This fact should match with the possible boundary condition that you have. And the possible boundary condition, the correct one, are you can apply only a pressure, a force, which is orthogonal to the external surface. You cannot have a shear force, a force which is parallel to the external surface. Because since inside you cannot have shear deformation, this is not allowed. If you make a model in this way, you are not able to obtain the solution. Now, someone said, okay, in this framework here, you see, I can give the boundary condition simply making some other assumption, and I can look what happened in the real object. The problem is that in the real object, you can have this kind of shear force in some case. So this is not the case, but for other cases, you can have very trouble to understand what happened. So simply observing the real object, one can say, but there is both the pressure and the shear force. So I am allowed to consider as a boundary condition a shear force. The problem is that if you consider the model of an ideal fluid, you cannot put on the boundary shear force because if you do that, the model that you write has no solution. So in order to have a model with coherent boundary condition, you cannot put any shear force on the boundary. But there are possible situations in which they are important in the real object. In fact, if these are important, you have to change the hypothesis of your model. You have to consider a model which is more complex of the ideal fluid. You have to consider a Newtonian fluid, which inside has some resistance to shear deformation, you know. So if you want to consider this kind of boundary condition, you have to change the model. You are not allowed to use the ideal fluid. And for the ideal fluid, it's very easy to understand what happened, but you can understand that if you consider a very complex situation, a very complex model, you are not so easy to say this boundary condition can be used, this boundary condition is not good, and so I cannot use. I mean, this is the point. And every time you use this framework, you have to deal with this kind of stuff. Instead, using this, you don't have this problem because all the boundary conditions are automatically given you by the definition of the energy. So you always have some mathematical problem which is well posed. Okay, I think that for today we can stop here. How to stop here? Okay.